Hey everyone, and welcome to The Explainer. Today, we are taking a seriously fascinating journey into the architecture of reality itself. We're going to explore how massive, interconnected wholes actually function and why they so often manage to completely surprise us. You know, we humans really love to feel like we're in charge. But as you'll see today, when you start combining diverse elements into a single system, you very quickly run into this wild phenomenon, the illusion of control.
It is just so incredibly tempting to believe that if you just map out every single nut, bolt, line of code, or individual person in a system, you can perfectly predict what the entire thing is going to do, right? It's kind of the ultimate reductionist dream. But we're going to shatter that illusion right now. Knowing the parts absolutely does not guarantee you know the whole. In fact, in the systems that matter most to our modern world, the whole behaves in ways the parts literally never could.
So, here's our roadmap for today. First, we'll untangle the crucial difference between complicated and complex systems. Second, we'll look at the specific drivers of system complexity. Third, we'll introduce the core phenomenon of emergence. Fourth, we'll break down the types of emergent behavior. And finally, we'll explore how engineers practically manage the unpredictable in the real world. All right, kicking things off with Section 1, Complicated versus Complex Systems. Okay, let's dive right into this. To truly grasp this concept, we have to look back at the scientist Warren Weaver, who noticed a massive gap between disorganized and organized systems. Think of a complicated system, like a high-end Swiss watch or a car engine. It's got hundreds, maybe thousands of parts. It might be incredibly hard to build, but at the end of the day, it's predictable, mechanical, and decomposable. If it breaks, you can just take it apart, find the broken gear, swap it out, and boom, it works exactly as it did before. A complex system, on the other hand, is more like a living forest, a global economy, or a city's traffic grid. These are nonlinear, adaptive, and highly dependent on their context. You can't just take an ecosystem apart to figure out why it's failing. The elements are constantly evolving and reacting to one another.
So how do we actually define this? Well, complexity is all about the richness, diversity, and interdependence of relationships. And I really want to emphasize this point. Complexity is not just about having a huge number of parts. I mean, a bucket of sand has millions of parts, but it isn't complex. Complexity is about the relationships between the elements and the system's relationship with its surrounding environment. It's all about that invisible web of connections.
Which brings us to Section 2, the drivers of system complexity.
If complexity is all about relationships, what makes a system cross the line from just being complicated to truly complex? Let's rapid fire through the 6 main drivers. First, interconnectedness, elements influencing each other through networks. Next, diversity, meaning the parts aren't all identical, they have different roles. Then, nonlinear interaction. This one is huge. It means a tiny, microscopic change over here can produce a massive, disproportionate effect way over there. Then we have feedback loops, which are constantly reinforcing or balancing out behaviors over time. Adaptation means the system literally adjusts itself in response to changes. And finally, context dependence, meaning the system is going to act completely differently depending on its environment. When you mix all 6 of these together, you get a system that effectively has a mind of its own.
Moving right along to Section 3, the phenomenon of emergence.
Now, when all those complex drivers we just talked about start interacting, a kind of structural magic happens that scientists call emergence. Basically, system-level properties or behaviors arise from interactions, and they cannot be attributed to any single component. Let's just pause on that for a second. This means there are properties in the universe that simply do not exist in the individual parts. They only exist in the organized whole. You couldn't find them no matter how closely you inspected the pieces.
To really ground this abstract idea, let's bring in the systems thinker Peter Cheklin. He put it perfectly when he said, entities exhibit properties that are meaningful when attributed to the whole, not to its parts. Cheklin is reminding us here that emergence isn't some mystical ghost in the machine. It is a very real, measurable reality of how nature and engineering actually work.
Let's look at some vivid, everyday examples to make this concrete. Take sodium, a highly reactive metal. Then you have chlorine, a toxic gas, but interact them together and the chemical compound that emerges is table salt, perfectly safe to put on your fries. Neither part is salty, right? The saltiness is emergent. Or look at flocking birds. Those beautiful sweeping patterns in the sky do not exist inside a single bird. Human consciousness emerges from a massive network of neurons, even though no single neuron is conscious. And think about this. Have you ever been stuck in a horrible highway traffic jam, finally reached the end of it, and realized there was no accident?
No construction, nothing. That jam emerged purely from the complex interactions, the braking speeds, and the following distances of the drivers. Literally no single car caused it.
Next up, Section 4, Types of Emergent Behavior.
Now, what's really interesting about this breakdown is that emergence isn't just one single thing. It exists on a spectrum. It ranges from outcomes we can easily calculate to massive surprises that totally blindside us. On one end, we have simple emergence. Its predictability is very high. A great example is the aerodynamic lift of an aircraft. Lift is emergent, it requires wings, air, and speed, but we have the math to predict it perfectly. In the middle, there's weak emergence. Here, predictability is low. This is your traffic pattern or stock market behavior. You can't predict it just by looking at one driver or trader, but you can run computer models to get a really solid guess. But on the far end is strong emergence. Predictability here is exactly zero until you actually see it happen. These are those unexpected, cascading failures in power grids or crazy unintended consequences in massive software networks. You literally only find out about them when they occur.
A lot of this weak and strong emergence happens because of what scientists call self-organization. This is when structure develops through local interactions, without any centralized boss telling the parts what to do. Thermodynamics actually shows us that ordered structures can emerge completely spontaneously in systems that operate far from equilibrium, meaning energy is just constantly flowing through them. The system essentially organizes itself to handle the flow.
So how does this actually come together? Well, emergence and self-organization don't happen in a vacuum. They're created when these four dimensions blend together. Structural organization, how things are physically or logically arranged; dynamic behavior, how they interact over time; information and control, the feedback signals that guide the system; and the environmental context, the outside world pushing in on the system. It's the constant, messy blending of these four dimensions that actually generates the emergent properties we care about.
Finally, Section 5, Engineering the Unpredictable. So, if systems are driven by complex relationships, prone to spontaneous self-organization, and capable of generating entirely unpredictable properties, how on earth do we manage the unpredictable? Honestly, this is the multi-trillion-dollar question for modern society. When you're building a global digital network, a nationwide power grid, or a smart city ecosystem, you are building a complex socio-technical system. You cannot fully predict it. So how do professionals actually go about taming this chaos?
Well, since engineers know they can't perfectly predict strong emergence, they rely on a very specific workflow. First, architectural design, creating smart boundaries and modular pieces to sort of contain the chaos. Second, modeling and simulation, running millions of virtual scenarios to try and force that weak emergence to reveal itself in the lab rather than out in the real world. Third, iterative development, building the system in small, testable chunks to see what emerges step by step. And finally, operational monitoring, recognizing that the system is going to do things in the real world that you absolutely didn't anticipate, so you just have to constantly monitor and adapt it while it's running.
And this brings us to the ultimate practical takeaway of this entire explainer. When you are dealing with complex systems, the goal is never to eliminate emergence. You can't, and honestly, you don't want to. Things like safety, usability, and resilience are themselves emergent properties. The goal of systems engineering is simply to increase the likelihood of desirable emergence while drastically reducing the likelihood and impact of harmful emergence.
We've seen how from super simple interactions, massive complexities arise, from bird flocks to traffic jams to global infrastructure. The illusion of complete control is exactly that. It's an illusion. But armed with an understanding of complex systems, we can definitely better design for a resilient future. So I want to leave you with this final thought. As our own engineered world becomes exponentially more complex, more intelligent, and more interconnected every single day, what unintended consequences are waiting to emerge next? Stay curious, keep analyzing the systems around you, and thanks so much for joining me for this explainer.